Hello, hello, hello. And here we go. Hey guys, welcome to Money Farming YouTube channel. In this video, I'm actually learning about DevOps with Python. So like all the images and every operations we do it for like Python application. Okay. So I'm gonna be learning from this Udemy course. You guys can check it out there. Um, so like. Um, so this course um, so I have this course on my other account, so I'm gonna play that one, and then you can understand. uh, it's just a like pair programming or like live coding. So let's just sit back and relax, and then yeah, so let's do it. Okay, so I'm gonna play the video.
Hello and welcome to Python in Containers course. Docker and Kubernetes are the must-have skills for Python engineers these days. Whether your goal is to learn Python for machine learning, data science, or to build cloud-native microservices, you inevitably end deploying your work in containers. Docker and Kubernetes skills are a key to become a respected and highly paid DevOps expert. In this course, you are going to learn using containers to package, deliver, and execute Python applications. It is very practical and has a lot of exercises. I think that examples and exercises are most productive way of learning. I strongly advise you to get hold of a laptop or desktop computer with Linux, macOS, or Windows. Not only listen and watch the lectures, but first of all, to do exercises. In Python in Containers, you learn to install and set up a development and execution environment to run your Python code in containers.
So this
Then
is what we're
you're
gonna
going
learn,
to
guys.
learn how to build container images with your Python code, how to ship them to other people, and how to run them. Finally, the course teaches how to run data science and machine learning tasks in containers. My goal is to make learning experience effective and affordable. I use open source or otherwise free software in this course. You're going to learn how to run your Python projects in containers on a development host, a laptop or desktop computer, but also in a production like environment on a public cloud. Let's look at the agenda now. The course can be consumed in many ways. For example, if your primary interest is in machine learning and data science, you can start with section 1 to get a general overview of Docker and containers, then take section 7 to get quick practical overview of how to run daily tasks in containers. Use remaining sections 2 to 6 to deep dive into specific topics related to Dockers and Kubernetes. First section delivers an introduction to containers. If you have never learned about containers or worked with them, you're going to get a necessary introduction to key concepts here. We're going to define containers. The cycle of build, ship, and run gets introduced and explained. We do an initial introduction to Docker and other container tools to get an overview of what is available for developers. This section is more of watching and listening than doing practical exercises. All further sections are very hands-on. I strongly encourage you to spend an hour or so to watch all of Section 1 lectures. It is building a basis of concepts and terms which we are going to use throughout the rest of the course. At the end of Section 1, you see how to containerize a simple Flask-based Python application. Once the container image is built, we ship it to Docker Hub image registry and then execute it locally using Kubernetes. The same container image with Python application is then executed in a public cloud. Section 2 of the course gives you a Docker deep dive. We started with a series of lectures about installing Docker in various operating systems. We focus on free version of Docker software called Docker Community Edition. You're going to learn how to install a container development platform on Ubuntu and CentOS
I'm gonna
Linux.
drink some Red Bull
We
today.
also learn how to set up Docker on Windows 10 Pro,
Wow.
which comes along with built-in virtualization named Hyper-V. If you don't have the Pro version, we also cover installation of Docker Toolbox on Windows Home. For macOS users, we have a lecture on setting up a decent Docker development environment as well. Once a Docker environment is up and running, we talk about how to work with Docker tools. We start with the images, then discuss how to run containers and manage them. Section 2 introduces container networking and storage and their implementation in Docker. Dockerfile Introduction lecture presents the automation of container image building. Next, we introduce the concept of image registry and use Docker Hub as an example. Then we have lectures about Python images, graphical user interfaces to manage Docker containers, and Docker machine. After this comprehensive Docker introduction, Section 3 teaches the core skill of building container images. We start the section with overview of key elements of containerized Python application, its lifecycle, and design principle. Then we have an important lecture showing manual container image build process. I show it on purpose so you understand better what is a container image and how it is created. Then we have a series of 14 lectures showing how to build images in an automated, repeatable, and fully controllable manner by using Dockerfile. Last part of Section 3 takes Django as an example Python application framework and discusses various aspects of network server applications. We talk about implementing production-grade database engine using application servers to run Flask or Django or similar, and how to build a bulletproof front end with proxy server. By end of Section 3, you will be able to design, build, and run complex multi-container Python application deployments. Section 4 focuses on delivering container images to the world or to operations team in your company. This way or another, it is about shipping container images with Python applications. We discuss the concept of image registry and learn how to use public registry of Docker Hub. Other image registries are also introduced and discussed in detail, for example, GitLab. This section also talks about automated image build pipelines, giving you a good introduction to continuous delivery. There is a lecture about image vulnerability scanning as well. Section 5 discusses running container images in Docker runtime environment. It starts with automation of multi-container deployments with Docker Compose. Then we discuss Docker Compose file format and how to use it. Docker Swarm is a container orchestration engine technology which enables us to run complex multi-container applications on clusters of Docker engine hosts. We discussed this technology in detail, so you're going to get good grasp of what it takes to run your Python application in production. Section 6 focuses on running containers in Kubernetes. This is currently the most popular container orchestration engine. My goal for this section is to give you, developer, deep understanding of how your Python application is supposed to run in Kubernetes environment. We talk a lot about declarative management approach and do plenty of exercises involving writing Kubernetes object template files. This way, you're going to learn how to describe your application deployment using Kubernetes YAML files. Section 7 shows practical application of Docker and Kubernetes to typical machine learning and data science tasks. We start the section with general discussion of using cloud-native tools in these areas. First practical skill you learn there is running Jupyter notebooks in Docker containers. You get detailed overview of how to create data science, research and experimentation environment with Jupyter, Anaconda, IPython, NumPy, SciPy, Pandas, Matplotlib, and the rest of the family in a Docker container in about 5 minutes. All you need is plain Windows, macOS, or Linux machine. For machine learning engineers, there are several examples of using TensorFlow containers for development and exploration of models. You also learn how to package a trained model into TensorFlow serving container image and run it as microservice in production environment. The section also has a lecture on running Docker with NVIDIA GPU acceleration. The course is going to teach you practical skills necessary to design and deploy your Python projects in cloud-native way. I'm so excited to get you on this journey to containers and clouds. Let's get it rolling with introduction of containers and key concepts related to them. In this lecture, I explain the idea behind the term container. We use this word every day, referring to a very complex concept, or we could say many distinct concepts. Of course, I mean computer term, not a bottle or a carton box.
I think I'm going to take some notes here.
Containers gives you a different answer. I think we can say that this is an overloaded term. Let's try to pinpoint the best definition. If we look up Google for the word container, first we get what is a container link from Docker Inc., the company behind one of the most popular container-related software. Text snippet says, a container is a standard unit of software that packages up code and all its dependencies so the application runs quickly and reliably from one computing and so on.
So, what is a container? A container is a standard unit of software that packages up code and all its dependencies so the application runs quickly and reliably from one computing platform. Okay.
Nice. But this is definition, it looks like a definition of a container image. This is pretty close to what I want. However, it's a kind of a narrow definition. Next result from Google search is a container definition at Wikipedia. Let's have a look at it. A container is any receptacle or enclosure for holding a product used in storage, packaging, and shipping. Things inside of a container are protected and so on. Well, this is a good one. Container holds a product in storage and shipping. Things inside of a container are protected. This is similar to Docker's container image definition, but a bit more general. In fact, it relates to anything that we can call a container, including a bottle or a carton box. We can say that container is a way to package and ship software. Docker says that it includes everything needed to run an application. We come back to this soon. We have a nice definition from Amazon Web Services. Containers provide a standard way to package your application's code, configurations, and the dependencies into a single object. Containers share an operating, and so on and so on. This one focuses on container image aspects again. I would like to highlight definition from CIO magazine. Containers are a solution to the problem of how to get software to run reliably when moved from one computing environment to another. This tells about software portability, which containers bring to us. We can easily pack our Python code along with all dependencies into a container image and ship it to other people. They can run such a container on any operating system supporting standard container runtime, be it Windows, various Linux variants, or macOS. The container image can be pulled from a repository and executed on nearly any operating system, delivering exactly same results. It can run on your development laptop, on a server in your organization's data center, or in a cloud somewhere over the internet. Each time you get the same results. Next result from our search is actually Google's page on containers. It says that every piece of software at Google runs in a container. Good point. So container is not only a way to package software, but also a way to run software. Here we touch a second most important meaning of a term, container. It is a runtime unit involving a kind of virtualization. Google's definition tells one more very important fact. Containerization allows our development teams to move fast, deploy software efficiently, and operate at an unprecedented scale. This is actually why Python developers think about containers. We want agility in development, efficiency in deployment, and ability to scale our code to the planet size, like Netflix or Spotify. Each week, we start over 2 billion containers, says Google. Wow, that's a lot of new software every week. Well, not necessarily. This tells us another important aspect of containers. They are short-living creatures. Unlike Greenland shark or African elephant, a container is spawned quickly, runs for a while, and most often is discarded and replaced by another container with a new version of the software. A typical container in a large-scale orchestrated environment has a lifespan of 12 hours. A container is more like a mayfly, which lives only one day. Let's summarize all aspects quickly. On one hand, a container is a way to pack your Python code along with libraries and dependencies into a self-sufficient software package. We call it a container image, to be exact. On another hand, a container is a runtime unit which executes the container image. Container images are portable and operating system independent. They can be executed nearly everywhere. The code packaged into a container is still processor architecture dependent. Containers isolate software at runtime. Python code in one container cannot directly access code or data in another container. They can communicate and exchange data, of course, but only in controlled ways. Containerization is the major change of software distribution. Once the code is packaged into a container and shipped to a registry, we run it simply by referring to its name and tag, URL or UUID. No need to install the software. We just have to have some sort of universal container runtime available. Containers enable agile software development with frequent deployment of new releases of our code. Tested and packaged into a container with new version tag, this makes a typical container lifespan shorter than 1 day. In most cases, a deployment is simply done by restarting a container with a new version of image. Containers at runtime depend on OS level virtualization and are different from virtual machines, which in turn depend on hardware level virtualization. You will soon learn much more about containers. For example, that containers can easily communicate with each other. Containers form a foundation of microservices architecture, which promotes decomposing of large applications into small, loosely coupled components. Organizations can establish many small development teams responsible for particular application or service components. The teams can deliver functional updates to their code frequently and mostly independent of each other. Resulting containers are small and compact, easy to spawn and restart. You can see that containers are a very clever concept, but I guess you can still feel that this is all new. All right, Docker is around since 2013, so containers are not that new. In fact, history of containers goes back to late 1970s, when Unix version 7 introduced first of tools to isolate processes, namely chroot. This tool allowed to change the root directory for a particular process to a subdirectory of server's file system. We dig deeper into this in the next lecture, so stay tuned. Container can be considered to be a software package and an execution unit. Let's focus on the first aspect now. Container image contains our Python code packaged together with Python libraries, installed with pip, and all other dependencies and components required to run our code. Have you worked with PyInstaller? It's a neat utility allowing you to package your Python application with libraries into a single executable. This is quite close to a container image. Everything you need to run your code is on one file. You can simply send this file to someone. This person is able to run the app without a need to install Python libraries or even Python itself. But there are some caveats in it. This executable can run only on the same type of operating system as the one you have used while packaging the app with PyInstaller. If you do it on Windows, you can run the .exe file on Windows only. It will not work on macOS, for example. Also, if you put some malicious code into your PyInstaller packaged application, let's say your code fetches a Trojan from a secret internet site, your app will gain enough access to somebody's computer to wreak havoc there. To understand container image better, let's look at the second aspect of containers, the runtime unit. When a container is executed on a host system, it gets its own file system, own network stack, and own process space. But it shares operating system kernel with host system and other containers running on the same host. Software running in a container is isolated from the host system and anything else running there. If you ship your malicious code in a container image, it potentially may affect the host system only when the person running this container explicitly shares host file system with the container. Otherwise, your app can fetch the Trojan and infect only the container itself. Once the person operating the host system deletes the container, everything in this runtime unit, including its root file system, is discarded and no longer available. Let me repeat this to make it as clear as possible. A host system with an operating system and container runtime installed can execute and run one or more containers. Each container gets its root file system, its network stack, and process space. All containers share a common operating system kernel. One container cannot directly see another's root file system, neither host's root file system. Each container has got its own IP address. A container can communicate with other containers via TCP or UDP using container's IP address and port number. Host system can be configured to allow containers to use host network stack to access the network and eventually the internet. Host system acts as a bridge and or a router for its containers. A process running in a container can see only processes in the same container. It cannot see processes in another container or in the host system. This means that each container has got its own unique process with ID 1 and so on. There are some important consequences of the fact that each container has got own root file system. One is that container cannot directly use any software installed on host system. You may have a nice and great Python development environment installed on your laptop. However, none of these can be used in a container you spin up on this system. When you package your Python application into a container, you have to make sure to include absolutely everything necessary to run, except of the kernel. No fear, it's quite easy. Container images are built in a way similar to Python classes. You get a so-called base image and build your image upon it, changing the base image in this way or another. Then you can use resulting image as a base image for another project and so on. We get into this in section 3 with much detail. Portability of a container image is the obvious advantage of this approach. Once you build a container image with your app and it runs well on your laptop, you can publish it and it will run the same nearly everywhere. All that is needed is just a container runtime, Docker, for example. There is a small print here. The base image of your container assumes certain type of host operating system kernel and processor architecture. Most of the container images you come across are based on Linux. These run perfectly well on Linux hosts but also on macOS and Windows hosts. There are some nice Windows-based images available from Microsoft. Various versions of Windows Server, as well as images with Microsoft applications installed, like IIS or SQL Server. All these goodies can run on Windows host systems only and do not run on Linux or macOS hosts. We will get deeper into Windows containers with some examples in section 2. All containers running on the same host share its kernel. When a container manages to hang a kernel, this fact is going to affect all containers. This is a disadvantage of containers and shared kernel. With this, you see that containers are considerably different than virtual machines. You may have seen this picture showing difference between virtual machines and containers. The fact that containers share the kernel with host system makes container start faster. There's no need to boot a kernel. On the other hand, virtual machine is nearly totally independent on host system. It has its own operating system and own kernel. If you boot a virtual machine for the first time, you usually begin with installing the operating system. In most cases, you install a complete server or desktop distribution. These are extremely universal, include tons of libraries and middleware software. Virtual machine with standard Linux system allows you to create users and require them to log in to gain access to the system. There is also a sophisticated bootstrap system included in standard operating systems to control the orchestration of many so-called system processes implementing system services. Remote login service or a graphical user interface in case of desktop system or a print service are good examples. All of these nice features are perfectly suitable when you run a host system, but become an unnecessary burden when you want to run a simple Python application. None of these extras are included in container-based images. These are designed for fastest possible startup. Most give you an option to install missing components in case your application requires something not included. Let's boot an Ubuntu Server 1804 virtual machine. Please notice how much time it takes to start. Looking at the console, you see a never-ending flow of messages confirming startup of service after service, up to the point when you get a login prompt. Now, you can get access to the system by entering username and password. Let's bring up an Ubuntu-based container to see how it is different.
All right, guys, let's get this going. So when I start my FreakAI server there, virtual VM instance. Oh, we have to explore Gemini as well. What do they have in like Gemini AI, man? I wonder what. Let's check this out. So Google AI Companion, Cloud AI enabled. Language powered by vision, speech. So all are different. Hello. Wanna learn about Gemini? Can you redirect me to some blog posts online? Yeah. See, why? I mean, they have like cut off to like November 2023 training data. I mean, it's ridiculous. I mean, Bing also gives like really good. I think yeah, Bing gives good response related to like internet search and all. So if I ask, um, uh, give me a blog post for learning about Google's Gemini AI. So it's gonna go to the web and then like okay, certainly Google's Gemini AI. Okay, represents Google's. See, this is what I like. Okay, so that you can like verify the sources too. See, blog.google skills.ai. Let's check out DeepMind. So welcome to the Gemini era. Chat with Gemini ecosystem represents. Yeah, it's good. Ultra Pro Nano. 3 different models, yeah. Where is Demis Hassabis? All these are product guys. Where is DeepMind CEO? Anyway, so we are installing NVIDIA driver there. It's a bit high-end machine that we're gonna be running a lot of. See, Google Deep Learning VM. I'm gonna be running a lot of pre-KI application there. So freak AI. So that's why I'm learning about this container. So we install the NVIDIA driver. How do I check it? NVIDIA SMI. And there we go. So we got 16 gigs of GPU memory, or RAM, you could say. And yeah, so it's Tesla T4, yeah. So do I have Docker? Yeah, I think so. Do I have Docker Compose? No, not Compose. Let's let's get this going, yeah. He talked about um Demis Hassabis. Gemini 1.5 or next generation model. Yeah, I think they have like million tokens or something. Yeah, it's really good. All right, let's continue.
What you notice here is that you simply get a shell prompt
Docker
and
run
it happens nearly
RT
immediately. List all processes
128
here and there with ps minus ef. Simply get a shell prompt and it happens nearly immediately.
IT means interact to
List
terminal.
all processes here and there with ps minus ef. Virtual machine runs more than 80 processes like timesync these, resolved, rsyslogd, etc., etc. Plenty of system services. At the same time, our Ubuntu container lists only 2 processes. Let's see how things are with Python. In our VM, we try Python 3. Voila, here it is. Let me do the most basic programmer's exercise. Print hello world. There you go. We've run some code in Python code in virtual machine. If I try the same exercise in Ubuntu container, I get an error. Python 3 command not found. Let's install it then. apt get update, apt install Python 3. Now I can successfully run Python 3 and print hello world. Let me exit this container and try to execute another, this time with Python-based image. Docker run Python 3. We go directly into Python interpreter prompt. Isn't it nice?
Okay. Instead of doing that, we can just like run from the Docker run it rm Python 3, get the layers, and there we have the Python. It's cool. Python. We got the this prompt here. So print hello world. Cool.
I can start the same container image with shell prompt. Now I can git clone a repository to my container and run some nice Python application. Let's see how a container runtime turns an image into a running container. An image consists of some metadata and a number of file system layers. Metadata simply describes an image in enough detail for container runtime to be able to launch a container. Container runtimes, Docker in particular, use so-called union file system to implement file system layers. We're going to analyze this topic in detail in the lesson on container images. For now, it is sufficient to say that image turned into a subdirectory tree in the host system is read-only. Docker Engine adds a thin writable layer on top of it to keep all changes container processes can possibly make in containers file system. In other words, when a container reads a binary executable from an uncompressed and expanded image, it reads it from the host file system. However, when a container writes data to a log file, this file is stored in this thin writable layer. Each container has its own writable layer, which is deleted along with the container at the end of its lifecycle. The read-only part of the image is shared among all containers using the same image. I hope this lecture gives you a decent overview of what is a container image and what is a container at runtime. In next lecture, we analyze the impact of containers on application lifecycle. In previous lecture, we took a closer look at container image and its instance at a runtime. Now, I would like to discuss with you a typical lifecycle of a container with Python app. Every good piece of code starts with a creative process. You need to have a good idea, do the design, and simply write the code. Containers are not particularly useful at this stage. You rather use a whiteboard, a notebook, maybe a pretty UML tool, certainly some sort of a text editor or a sophisticated IDE, possibly a version control system like Git or something. Sooner or later, you have some code you would like to execute to see if it works. This is when you can finally get containers useful. In section 3, we look at ways of using containers to have a clean Python runtime environment for development and testing.
Such environment is easily disposable and replaceable when things go wrong. Once the code is ready to be shipped from development to test and eventually to production environments, you package it into a container image. This is a build phase. There are many ways you can actually build a container image. You can do it manually, let's say. Start a container with a selected base image, maybe a pure play Linux distro like Ubuntu or CentOS. Once you get a shell prompt, install necessary software components, most likely Python, PIP, and libraries. Then you copy the software from Git or other software repository and run what is required to initialize software environment. At this stage, the container includes everything necessary to run your application. You may do a test run in order to verify this. If Docker is the container software in your dev system, you simply exit the container and freeze it into a container image. Such manual image build process is okay, however, may be difficult to repeat when the software becomes more complex. Good for us, there are tools enabling container image build automation. Docker build command is the most common example. Instead of manually executing a series of commands, we write a special script called Dockerfile. In this script, we put all configuration details of our image, as well as all commands required to prepare an image. Once the Dockerfile is created, we can simply run Docker build. Docker runtime creates a temporary container, executes the script in it, and freezes it to create the desired image. You can put the script along with your code in version control system. This way, you have a totally repeatable way to recreate versions of your packaged application. Section 3 deep dives into the build phase. When the image is built, it is ready to be executed in container runtime environment. However, it is still residing at your development system. You need to ship it to an image registry to make it available to be pulled into a destination runtime system. There are many possible options to store container images. One of the most popular is Docker Hub. Other public repositories are also available. Most of public cloud providers offer their image registry services. If you plan to deploy your containerized app on Google, for example, then their gcr.io is an interesting option. The same goes for Amazon Web Services and others. Cloud providers have an option to store images in public registry so everyone can use them, or in private registries where you can control accessibility of your images. In case you plan to deploy images in private cloud or simply on your own runtime environment, you may consider setting up a private container image registry on one of your servers or clusters. It is a quite painless and quick process. We discuss image shipping in detail in section 4. Once an image is built and shipped, it should be run. We need a suitable runtime environment. The beauty of containers lies in the fact that they can run nearly everywhere. Later in this course, you see same container image deployed on a simple development laptop, then on a Linux server under my desk, and then on a cluster at a public cloud provider. Once the Python app becomes complex, let's take a Django-based application as an example, we split it into a number of separate containers. Container best practices suggest container. Container best practices suggest keeping each container simple and small and serve just a single purpose. This leads to a complex system of interconnected runtime units, load balancers spreading incoming traffic over a bunch of web servers, web server containers accepting client connections, terminating HTTPS, and routing requests to WSGI application servers running our specific Python code in WSGI environment, database clusters for high availability, virtual networks interconnecting our containers and segregating classes of traffic, persistent volumes to store database files, static data for web service, etc. This approach allows us to perform rolling update of components like web servers, for example, Nginx, without stopping the whole application service. It's important to notice that we can do this upgrade without rebuilding or even touching application servers or other runtime units. We can deploy new features of our application by rolling restart of application servers with new version of container image. If a nasty bug happens, we do a quick rollback of application servers to a previous image version. Modern container runtime environments like Kubernetes or Docker Swarm enable sophisticated orchestration of complex container services and make operations agile and robust. Most of the orchestration can be scripted and again stored in version control system. Great tools like Jenkins or Travis help automate full deployment pipeline. Once you push your code to version control system, it triggers automated tests. If these are passed, images are built automatically and deployed into production in the same way. This is DevOps at its best. We discussed these subjects in sections 5 and 6. I will show you how to containerize a simple Flask application, ship it to Docker Hub, and run in several different environments in further lectures of this introduction section. Previous lecture discussed many container-related tools. Now we introduce Docker tools and discuss them a bit deeper. We're going to use Docker throughout this course because Docker tools are simple to use and understand. It's available on many platforms. Section 2 explains how to install and use desktop to build images, ship them via Docker Hub, and run them on Windows laptop, both Windows Pro and Windows Home Edition, Mac OS system, and Linux. Containers built with Docker tools can run on nearly any container platform, including most of public cloud container services. Docker Community Edition is free, so there is no additional cost to learn a lot about containers. Docker Toolset is quite comprehensive and covers a lot of processes related to development and management of containers. I'm not affiliated with Docker Inc., and I have no direct or indirect interest in making you use Docker products. My only goal here is to give you a thorough, exhaustive, and practical knowledge of containers. I consider Docker to be a very good starting point for a beginner in a container world. Docker tools are most popular and probably easiest to use. There's plenty of knowledge related to these tools quickly available on the internet. I mention and show alternatives throughout the course, so you should get a pretty broad view of other tools as well. Docker started as a project at .cloud, the company founded by Salomon Hykes in 2010. It's been presented to public during PyCon Santa Clara in March of 2013. Please check Solomon's talk at this link. Docker software has been released as open source in the same month. .cloud has been renamed Docker Inc. in October of 2013. Since then, Docker Inc. developed the software and extends it with acquisitions of interesting startups. Orchard, a tiny company who developed multi-container orchestration tool, has been acquired by Docker in 2014. Their technology, called PIG, formed the basis of what we know today as Docker Compose. You can check Docker website for company's milestones. Docker software is available either as Enterprise or Community Edition. First is a commercial product. You pay for license and maintenance and get some extra features useful in larger enterprise environments. The Community Edition is backed by open source developer community. It is free to download and use, and there is no support from Docker Inc. in case you find a bug or a serious issue. Let's do an overview of key Docker tools, starting with Docker Engine. This piece of software is a famous Docker command plus few bits and pieces to make it do the job. You can start and stop containers, you can build them and push them to a container registry. It also enables management of virtual volumes and networks used by containers. Engine is available for various Linux distributions and for Windows Server. Engine functionality is also a part of Docker Desktop for Windows and Mac, although it is implemented slightly different there. If your system cannot run Docker Engine natively, you still can enjoy nearly the same user experience with Docker Machine. Its primary role is to provision virtual machines with custom Linux imaging, curated by Docker Inc. Such a virtual machine runs a Docker engine, which is managed with Docker command. Later in the course, we use Docker Machine to provision 3 virtual machines with Engine in order to play with cluster of nodes. I discuss more of interesting Docker Machine details in section 2. Docker Compose allows management of multi-container applications in a coordinated way. Apart from relatively simplest apps, you will split your work into a number of containers. For example, one for a web server, one for WSGI application server, and one for a database engine. Docker Compose introduces compose file where few simple lines of YAML code define such multi-container applications with necessary runtime environment artifacts. Docker Swarm goes few steps farther into container orchestration. You can define and run an application stack with multiple services, virtual networks, volumes, configuration files, secrets, etc. Each service is made of one or more containers. Swarm can scale each service independently, adding more replicas or simply container instances of a particular image, or decreasing number of replicas in a service. Swarm also enables a controlled upgrade of software running in a service. Existing containers are stopped and restarted with new image. This can be done one at a time to implement so-called rolling upgrade. Swarm can be compared to Kubernetes, although seems to be less capable. We look closer at container orchestration in next lecture. Docker Hub is a registry as a service available at hub.docker.com. We use it to get access to base images. When you start a container with particular image, let's say a famous hello-world, Engine pulls it off Docker Hub. Here, I describe a default engine configuration, of course. Once you create an account with Docker Hub, you can push your images there, and others can run your software by simply pulling it from Hub. There are other container registries available. We talk about it extensively in section 4. Docker registry is a quick way to set up a local container registry. Although you can create private registries at Docker Hub, there are situations when you may want to have a local on-premise registry to store your container images. Docker Registry is available as a community edition software with pretty sophisticated functionality. It is also a part of Docker Enterprise Edition, where it is called Docker Trusted Registry and has some more features related to security. Both Docker Enterprise and Docker Desktop are software bundles, combining a selection of tools for better user experience. In this course, we're going to use Docker Desktop as our primary work environment for container development. It is available for Windows Pro and Mac OS. There is an enterprise version of Docker Desktop available. This is out of scope for us, at least now. This version would be suitable for use in larger development teams requiring the capability of remote software management on development workstations, as well as tight security. We focus on Community Edition in our course. So what is included in Docker Desktop? First, there is Docker Engine. All of its functionality is performed with Docker command line utility. I think it is worth to explain here that Docker Desktop runs Docker runtime in virtual machine on Mac. This is also the case in desktop for Windows when you run it in Linux containers mode. We're going to use this mode throughout most of the course. This virtual machine runs simple Linux with Docker Engine. So, in fact, Docker Desktop runs containers on Linux. There is also a Docker Compose for multi-container deployments. What about graphical user interface? Frankly, there is no real graphical user interface included in Docker Desktop. Docker is for nerds. You do things on command line. Okay, there is a simple tool named Kitematic. I will show it and discuss its functionality in section 2. If you really prefer to work in graphical user mode, there are some pretty good ones available in open source. More on this in section 2 as well. Let's continue with Docker Desktop. Another important component of Docker Desktop package is Docker Swarm. Docker Desktop can also install and start a simple single node deployment of Kubernetes for container orchestration. There is also Docker Machine included. As you see, a Docker Desktop is a full bundle of Docker tools. You get nearly everything you may need to work with containers. Docker Enterprise Edition, on the other hand, is a product for enterprises intending to run containers in production and at larger scale. Enterprise Edition includes a number of management and security-related tools. If you need a highly available vendor-supported containers as a service platform, Docker Enterprise Edition is a solution to consider. Container orchestration is a major topic once your application grows in size and attracts more and more users. Let's talk about it in next lecture.
All right, guys, I'm gonna stop the video here. It's over 1 hour, 10 minutes. So yeah, I'm gonna continue later on. Okay.